Hello everyone. In this video we will see some free body diagrams for different problems. I have taken the diagram from those type of the problems where they will ask to calculate the reaction forces. Now the point is how you will calculate the reaction forces for that particular body from the free body diagram. Generally for every body, as there will be supports, you can draw the free body diagram by eliminating that supports. Once you get the free body diagram, for that free body diagram you can draw the rectangular components force diagram. From that rectangular components force diagram, you can take the horizontal components and vertical components. And we know that every body will be in the equilibrium condition. If it is not in the equilibrium condition also, we can get back the body into the equilibrium condition. So when it is in the equilibrium condition, it should satisfy the equilibrium conditions like sigma h, sigma v and sigma m is equal to 0. By using these three conditions from the rectangular components force diagram, we can calculate the reaction forces. So this is the procedure. First of all, for every problem there will be one free body diagram. For that free body diagram, you can draw the rectangular components force diagram. From that rectangular components force diagram, if you equate sigma h and sigma v is equal to 0 or sigma m is equal to 0 according to the given data, we will get the equations. By solving that equations, you can calculate the reaction forces for that particular body. Now we will see some examples. This is one of the diagram which is given in the question only. Now here see the diagram. Here how many supports are there? Here dashed line is the indication for the fixed support only. So here one support is there, and from A to C, which is nothing but a bar. So bar is also a one kind of support. So here two supports are there. So by eliminating, by removing these two supports, you will get the two reaction forces in the free body diagram. And in this problem, in this diagram, two direct forces are there. So you will get the two direct forces in the free body diagram. So here two direct forces are there and two supports are there. From the two supports you will get the two reaction forces. So completely four forces you will get in the free body diagram. So in the free body diagram, once again project the ball diagram once again, and here draw project the direct forces once again in the free body diagram. So here W is there. W is the weight of that particular ball which is acting in the downward direction. Next here P is the second force which is projecting towards the positive x-axis. So here write directly P. Next here coming to the first support. This support, this horizontal support is acting on the ball in the upward direction. So in the upward direction, which in the perpendicular direction to this horizontal plane, you will get one reaction force. And here B is the point of the contact between the horizontal plane and the ball. So you will get R suffix small b. Next one. Here AC is nothing but a bar. And we know that wherever you get the bar, you will get a bar or a string or rope type of the supports. You will get a tensional forces. Which will act away from the body. So here AC is a bar and it is in the third quadrant, and you will get a tensional force which acts away from this ball. So you will get one tensional force which is acting away from the ball and it is going into the third quadrant, and we can represent with any alphabetical letter. I will represent with S. So here two direct forces W and P from the main diagram, and here one support is there. From this support you are getting the RB reaction force, and from this bar support you are getting the tensional force S. So this is the free body diagram for this body. Next, coming to the second example, here observe the main diagram. Here one ball is there, and here W is the weight that is already given in the question, and here one string is there. AC is the first string. Next here AB is the horizontal string. AC inclined string, AB horizontal string. To these two strings, here P and Q are the loads which are attached to these strings with the help of this pulleys, supports. Here one pulley is there, here one more pulley is there. So these two are the supports. So for this diagram we should draw the free body diagram. Here for this main diagram, here W is the direct force. So you will get one direct force W, and then according to the question, here one more support is there. Dashed line is the indication for the support only. So here first one, second one and third one, three supports are there. So from these three supports you will get the three reaction forces in the free body diagram, and one more direct force is there. So 3 plus 1 4, completely you will get 4 forces in the free body diagram. Now here when you remove this support, this load Q load will act along the string, and this string is in the first quadrant. So and this by removing the string you will get a tensional force which is acting away from the body. So this Q load is acting along the string. If you remove this pulley and if you remove this string, you will get a tensional force which is acting away from the body, and this is in the first quadrant. So you will get the one reaction force, tensional force in the first quadrant, which is nothing but Q force. Next, here if you remove this pulley, this P will act along the horizontal string AB, and if you again remove this string, you will get one tensional force which is acting away from the body, and this is acting along the horizontal axis and it is going into the negative x-axis. So towards the negative x-axis you will get one reaction force, tensional force, P force. Next, here this dashed line is the indication for the fixed support only. So this support is acting on the ball in the upward direction. So in the upward direction you will get one reaction force RD. So here D is the point of the contact between this support and the ball. So you will get R suffix small d. So one direct force W, and this support is acting on the ball in the upward direction. So you will get one reaction force RD, and by eliminating these two supports, these loads will act along the strings, and if you eliminate that strings, you will get the tensional forces which are acting away from the body. So in the first quadrant from this string you are getting the Q support, Q force. Next, by eliminating this string from this load, you are getting the horizontal force which is acting towards the negative x-axis, P force. So this is the free body diagram for this diagram. Next, coming to this diagram, here two rollers are there, two balls are there. P is the first one and Q is the second one. Here completely this groove is nothing but a fixed support only, and we should draw the free body diagram for the P ball separately and Q ball separately. First of all, we will see the free body diagram for the Q ball. Now see here, for the P ball, you check how many supports are there. For the P ball, here this is in the contact with this support. So and A is the point of the contact between this vertical wall and this ball. So here one support is there. And next one, when you consider the when you are drawing the free body diagram for the P ball individually, Q ball will act as a one of the supports for the P ball. So this Q ball is second support. Only two supports are there. So from eliminating these two supports, you will get the two reaction forces. Now here weight will always act in the downward direction, so that is the direct force W. So completely three forces you will get the free body diagram for the P ball. So here W, which is acting in the downward direction. Next one, this support is acting on this ball in this direction. In this direction means towards the negative x-axis. So towards the negative x-axis you will get the reaction force R suffix small a, as A is the point of the contact. So R suffix small a. Next one, Q ball is acting on the P ball and it is going into the first quadrant. So in the first quadrant you will get one reaction force RE, as E is the point of the contact between the P and the Q ball. So R suffix small a. And as it is in the inclination according to the similar angles, here alpha is equal to here alpha. So this is the free body diagram for the P ball separately. Now coming to the Q ball, see the supports for the Q ball. How many supports are there? Here one support is there, here one more support is there, and P ball will act as one of the supports. So this will be also considered as one more support. So three supports are there and one direct force is there. So completely you will get four forces in the free body diagram. So weight which is acting in the downward direction, that is the direct force W, and here this support acting on this ball in this direction. In this direction means positive x-axis. So you will get one reaction force which is directing towards the positive x-axis, RB, as B is the point of the contact. Next, this support is acting on the ball in the upward direction. So in the upward direction which is directing towards the positive y-axis, you will get one reaction force, R suffix small d, as D is the point of the contact. Next, P ball acting on the Q ball and it is going into the third quadrant. So in the third quadrant you will get R suffix small e, as E is the point of the contact, so RE. And according to the alternate angles, here alpha is equal to here alpha, and RE in both the free body diagrams for the P and the Q ball, those magnitudes will be equal only, but which will act in the opposite direction. Why? Because P ball acting on the Q ball and Q ball acting on the P ball, reactions will be same only. So here RE in the free body diagram and here RE in the free body diagram of the Q ball, magnitudes will be equal, but they will act in the opposite direction. As it is going into the first quadrant, it should go into the third quadrant. So these are the free body diagrams for the P ball and Q ball for this diagram. Next, coming to the next example, here observe this diagram. Here one direct force is there. Next, here one roller support is there, and here one more pin support is there. So from the from these two supports you will get the two reaction forces. So here by removing this roller support you will get one horizontal force. So this support is acting on this bar. This is nothing but a bar only. This support is acting on the bar in this direction. In this direction means towards the positive x-axis. So you will get R suffix small b, as b is the point of the contact. So R suffix small b. Next, here direct force is there which is acting in the downward direction. Next, here whenever you get the roller supports, you should think about the complete diagram. As this is a linked part, when this is in the rolling position, complete diagram will move in one direction. So when it is moving in the downward direction, this part of the diagram will move in the upward direction and it will go into the second quadrant. So in the second quadrant you will get one reaction force by eliminating this support. So you will get one reaction force which is projecting towards the second quadrant, RA, with some inclination. And one more thing, wherever you get this type of the complicated supports, you can cross check your free body diagram whether your free body diagram is right or wrong, and like by using the equilibrium conditions only. We all know that every body should be in the equilibrium condition. When it is in the equilibrium, it should satisfy those equilibrium conditions like sigma h and sigma v is equal to 0. Now in the free body diagram you identify how many horizontal positive components are there and horizontal negative components are there. Here RB is projecting towards the positive x-axis, so one horizontal positive component, and here as it is going into the second quadrant, it will be resolved into two components, vertical component and horizontal component. So here RA horizontal component and it is projecting towards the negative x-axis. So here one positive horizontal component and here one more negative horizontal component. So this is balanced by this one. So sigma h is equal to 0. And coming to the vertical components, here P force is projecting towards the negative y-axis. As it is going into the second quadrant, you will get one vertical force in the upward direction. So this downward vertical component of the force is balanced by the vertical component of this RA. So that is nothing but sigma v is equal to 0. Number of horizontal component forces is equal to 2. One positive component, one negative component. Number of vertical components is equal to 2. One negative component, one positive component. So vertical components are balanced and horizontal components are also balanced. So this is the balanced condition system. So we can cross check our free body diagram by using the equilibrium condition, and our free body diagram is right. Next, coming to the last example, here one more problem is there. Here one support is there, here direct force is there 120, and here pin is there. Pin is nothing but a one kind of a support only. For this bell crank body, here one support, pin support is there. So we should eliminate this support. So here one direct force is there. So you will get the direct force as 120, which is projecting towards the negative x-axis. And here one support is there. So this support is acting on this linked bar in the upward direction. So in the upward direction, you will get one RA reaction force. As here A is the point of the contact, you will get R suffix small a. And here when you eliminate this pin, when you remove this pin, this bell crank will project in the downward direction and it will go into the fourth quadrant. So in the fourth quadrant you will get r suffix small b, as b is the point of the contact, so you will get r suffix small b. Now again you can cross check the free body diagram by the equilibrium conditions. Like in this problem, how many horizontal components are there? Here one horizontal component is there and it is having some inclination, so RB will be resolved into two components, one horizontal component, one vertical component, in this way. So here 120 is the negative horizontal component. From this RB in the fourth quadrant you will get one positive horizontal component, so this is balanced by this one. Next here RA is going into the positive y-axis, and here from RB you will get one vertical component which is projecting towards the negative y-axis. So this positive is balanced by the negative vertical component. So number of horizontal components is equal to 2, one is positive and one is negative. So both are balanced. And again number of vertical components is equal to 2, one is positive and one is negative, both are balanced. So all the components are in the balanced condition and our body is in the equilibrium condition. So our free body diagram is right. Generally for the simple supports there is no need of cross checking the free body diagrams. From the direct supports you will get the direct reaction forces. Wherever you get the supports you will get the reaction forces in the perpendicular directions, and wherever you get the supporting elements like bar, strings, you will get the tensional forces which will act away from the body. So there is no usage of cross checking the free body diagram. For complicated types of the supports only you can cross check the free body diagram, whether our free body diagram is right or wrong, by using the equilibrium conditions like sigma h and sigma v is equal to 0. These are some of the examples for the free body diagrams in the problems. Generally these are the different problems, different diagrams which I have taken from the problems only. In every problem generally they will ask to calculate the reaction forces. Like in this problem they will ask to calculate RB value or P value. How can we calculate RB and P value? By using the equilibrium condition. If you equate all the vertical components is equal to 0, you will get one equation. If you do all horizontal components is equal to 0, you will get one more equation. By solving that two equations we will get the RB value and P value directly by solving them. In the second free body diagram also they will generally ask to calculate the P or Q or RD or Q according to the given data. In the given data some values will be given. They will ask to calculate the reaction forces. We can calculate by using the equilibrium conditions. In this one they will ask to calculate the RA and RE. In this one RE and RD and RB. And one more thing, for such a type of the problems generally here two balls are there. P is the first ball and Q is the second ball. Here for the P ball three forces are there. Out of the three forces W value, magnitude value will be given in the question. So two unknown values are there. Here out of the four forces, here one value is the known value. So three unknown values are there. So first of all we should calculate the problem according to the less unknown quantities. For the P ball two unknown quantities are there. For the Q ball three unknown quantities are there. So select the ball which has less unknown quantities and draw the free body diagram for that ball and do the procedure to calculate that two reaction forces unknown quantities. After calculating that problem you can substitute that RE value in the second free body diagram for the Q ball. If you substitute the RE and W, there will be two unknown values RD and RB. Again you can calculate these two quantities by the equilibrium conditions. So select the ball which has less unknown quantities and you proceed for the later procedure. Next, for such type of the complicated problems they will ask to calculate the RB value or RA value, P value. Some values will be given in the question. They will ask to calculate some more reaction forces from the free body diagram. If they ask to calculate any one of the forces from the free body diagram, there will be only one procedure by using the equilibrium conditions only. These are the complicated problems, first problem and second problem. Once again, for every problem, first of all you need to draw the free body diagram. For the free body diagram, next you need to draw the rectangular components force diagram. From that rectangular components force diagram you can get all the horizontal components and all vertical components. From that horizontal components and vertical components, you can use the equilibrium conditions like sigma h and sigma v is equal to 0. From that equations you can solve the problem and you can calculate the reaction forces from the free body diagram for that particular body, and every body should be in the equilibrium condition. If it is not in the equilibrium also, we need to get back that body into the equilibrium condition by equilibrium conditions like balancing conditions, like positive quantity should be equal to negative components. So these are some of the free body diagrams for different problems.